Hello students, today we are going to start a new series of discussion for class 12 students on physics. We call this series as quick recap series. We'll take a chapter-wise discussion, and in each chapter on all topics of that, we'll go through the detail of that. We'll take some conceptual type questions based on that so that your concepts are clear. And we'll also take numericals on that so that whatever theory we have done, we can apply it to the numerical problem. So let's start our quick recap series discussion on electrostatics. This is our first part of the discussion on electrostatics. And in today's discussion, we'll take frictional electricity. We'll take the methods of charging, that is the different methods of charging, charges and their properties, Coulomb's law in vector form, superposition principle, and some conceptual type questions, and after that we'll take some numericals also. Frictional electricity. Now, frictional electricity is the phenomena in which charges are developed on two bodies when they are rubbed together. You have two bodies there, and if you rub them together, you will find that there are the charges developed on the two bodies. The charges developed on the two bodies are equal in magnitude and opposite in nature. And this is basically due to the transfer of the electrons from one body to another. Let's take an example. If you have a glass rod and if you rub it with silk, then positive charge is developed on the glass rod and negative on silk. Another example, if you have an ebonite rod and if you are rubbing it with fur, in that case on ebonite rod, there will be negative charge developed, and on fur there will be positive charge developed. The charges developed is basically due to the transfer of electrons. The body which will lose electron will become positively charged, and the body which will gain those electrons will become negatively charged. And how we get that if the two bodies are rubbed, which one will become positively charged and which one will become negatively charged? This you can easily get it from triboelectric series. Now in this series, you can see there are many materials mentioned here, and if you take any two, in that case the one which will appear first in the list will become positively charged and the other one will become negatively charged. If you take glass and if you rub it with polyester, as the glass is appearing above in this particular series in respect to the polyester, so glass will become positively charged and the polyester will become negatively charged. Similarly, if you take any other, or if you take say nylon and if you rub it with paper, in that case nylon will acquire positive charge and paper will have the negative charge. So here with this triboelectric series, you can get that if the two materials are taken, which one will become positively charged and which one will get negative charge there. Now let's take frictional electricity. Suppose we take two glass rods and we suspend them by means of a thread, and it is kept side by side. If they are uncharged, in that case they will lie in any orientation. Suppose we take this one, this is the first one, this is the second one, they are lying in any orientation. But here, suppose if I rub them, suppose we have rubbed the glass rods there with silk, and say one end is rubbed here, in that case we find that there is a repulsion between the two. Similarly, if you take two ebonite rods and if you rub them with fur and if you suspend them side by side, in that case again there is a repulsion. But when we take a glass rod and another one we take an ebonite rod, and glass rod one end is rubbed with silk and ebonite's one end is rubbed with fur, in that case there is attraction between the two. And if they happens to touch one another, after touching it, they can lie in any orientation or they slightly repel one another. This is the observations which have been done on this frictional electricity. And with these observations, they have come to conclusion that the bodies possess charge. And it is of two types. Why is it so? Because if suppose you take there is a repulsion, by that time it was only the gravitational force which was known. Gravitational force cannot be the cause of this repulsion because the gravitational force is attractive force. And here we notice that a glass rod and ebonite rod, when they are rubbed, and they are attracting each other. So obviously it cannot be due to the mass there. That means gravitational force cannot be the cause for that. Because this one we notice only when they are rubbed. If it is only mass, in that case, they could have got attracted there in any orientation or in any case there. Not only after rubbing. So with that, they have concluded that due to rubbing, there must be some change in the material or something is happening there. And whatever is happening in glass rod is different from what is happening there in ebonite rod. So that means the changes are of two types. And then they concluded that it is due to the charge. And also the charges are of two types. So the importance of the frictional electricity is that this was the experiment which has first suggested that there are the charges possessed by the body. And secondly, that the charges are of two types. Now let's see what are the charges there. Electric charge is the property of the subatomic particles that causes it to experience of force when placed in electric or magnetic field. So it is basically a fundamental and intrinsic property of matter. And electric charges are of two types. One is the positive and other is negative. And we say that positive charge is due to the loss of electrons from the body and negative charge is due to the gain of the electrons in the body. So it is basically due to the electrons there. Because the electrons will be the one which they will either lose easily or they can accept it. So if the body is positively charged, it simply means that there is a deficiency of electrons. And if the body is negatively charged, it means it has surplus of electrons there. Charge is a scalar quantity and the unit of charge is Coulomb. So this is some basic idea about the charge. And now let's see the different methods of charging the body. So the different methods which are there, one is the frictional method, other is the conduction method, and third one is induction method. Frictional method we have just discussed. So when the two bodies are rubbed together, the charges which are developed on the two bodies, they are equal in magnitude and opposite in nature. The body which is losing electron will become positively charged and the body which will gain electron will become negatively charged. So this is there in frictional method. Let's take conduction method. Here in conduction method, what we do, we take a charged body and we bring it close to an uncharged body. Normally a conductor which we are taking. And here, this is suppose the first one, we have shown that this is the charged body, it has a positive charge here. And this is your uncharged body. So second one is your uncharged body here. And we are bringing the charged body and we put it in contact with the uncharged body. In that case, the charges will be shared between the two. And here, why there is a sharing? Because the two bodies there will be at a different potential. The body which is charged, it has a higher potential. The body which is uncharged is at, say, zero potential there. So when we are putting them in contact, in that case, the charges will move from high potential to low potential. And that flow will make the charges to get shared between the two. And this flow of the charge will continue till the two bodies acquire equal potential there. So that means the charge will flow only till the moment there is a potential difference. The moment the potential difference becomes zero, there will be no further change. And remember, if the two bodies are there having same size, identical bodies are there, one is charged, other is uncharged. When they are put in contact, in that case, the charge will be equally shared. But if the two bodies are of different sizes, in that case, the charge will be shared differently by the two bodies. Because their potentials there, due to their size, will be different if I take particular amount of the charge. So once the potentials are equal, in that case, there will be no further change of the charge in the bodies and that particular moment, the two bodies will have the different amount of charge if their sizes are different. So this is by conduction method. And one more thing you remember, that by conduction method, the bodies will acquire the same nature of the charge. Let's now take induction method. Now in induction method, what happens? We have a charged body. This is suppose your uncharged body. We bring the charged body close to uncharged body without touching it. So there will be no contact between the two. And when you have the charged body brought close to it, in that case, what you will find that there will be opposite nature of the charges. Like if it was positive, it will be the negative charge which will be developed on this side, that is the nearer end, and same nature of the charge will be developed on the farther end. So these charges are developed, and these we call as the charges which are induced here. Remember, the opposite nature of the charges which are developed on the nearer end, they are called as the bound charges. These are the bound charges. Whereas these charges which are developed on the farther end, we call them as the free charges. Suppose we earth this one. So the moment you will earth it, what will happen? These charges which are positive, they will disappear. Now why they will disappear? Because the electrons from the earth, they will move towards this body and they will neutralize these positive charges. As a result, now these positive charges will disappear. And after that, if you remove this charging body and then you remove the earthing also, then this body will acquire the negative charge. Remember that if you want it to get negatively charged, that is the other body to acquire a negative charge, in that case, we have to earth that one. And after that, we can remove the charging body as well as the earthing. Then it will acquire the negative charge distributed all over it. But here, there will be one more question there. Now, suppose we earth this portion, then what will happen? Is it that the negative charges will disappear? And if you remove the body and the charging body and the earthing there, in that case, the body will become positively charged? No. Remember, as long as the charging body is present, no matter which side of the body on which the charges are induced, are touched or earthed, it is always the free charges that will move and not the bound charges. So it will be, again in this particular case also, it will be the positive charges which will disappear and not the negative charges. So this is there in the induction method of charging. Let's now take the properties of the charges. The main properties of the charges which we take are like charges repel and unlike charges attract. Then charges are quantized in nature. Charges are additive in nature. Charges can be induced. Charges are conserved. And charges are invariant. Let's discuss these properties one by one. Like charges repel and unlike charges attract. Like suppose if I take that we have the two bodies which are having the same nature of charge. Suppose they are having the positive charge there. In that case, there will be repulsion. So in this case, you can see that there is a repulsion between the two bodies that we have shown. If the two are carrying, say, negative charge there, in that case, there will be again repulsion. So here again, it is the repulsion there. But if you consider that this particular body, which is having positive charge, and this body has a negative charge there, in that case, there will be attraction. So this one will get attracted. So there is a force of attraction if the two bodies are carrying opposite nature of the charges there, or they are carrying unlike charges. Next is there, charges are quantized in nature. What is that? Quantization law simply says that the charge possessed by a body is integral multiple of certain minimum charge. Using this quantization, we can write this one Q as plus minus N. Like here, Q is the charge on the body. So this is the charge on the body. N is an integer and E is the smallest unit of charge. This is the smallest unit of charge. And at this moment, we take the charge on the electron as the smallest unit of charge. So here, E will be equals to 1.6 into 10 to the power minus 19 Coulomb. That is the electronic charge there. So if a body is charged, it will have the charge only as integral multiple of charge on the electron at this particular moment, because this charge on the electron we consider as the smallest charge. Do remember, never say that quantization law as the charge possessed by a body is integral multiple of charge on the electron. Although we use this expression Q equals to NE for solving numericals and other, but there E is at this moment we are taking as the charge on the electron, but basically it is the smallest unit of charge. In future, if some other particle is considered that they are the one which are carrying the smallest unit of charge, which is less than the charge on the electron, in that case, that E value will change to that particular particle. So here, it is the integral multiple of certain minimum charge, not the charge on the electron. Although for solving numerical, we take it as E. That is the charge on the electron. Next property is charges are additive in nature. Now, what does it mean? The net charge possessed by a body is algebraic sum of the charges given to the body. That means we take that Q as summation small q. That means if you have a body, you are giving the different amount of charge on the body. In that case, the net charge on the body will be the algebraic sum of the charge which is given to the body. Like you have suppose a body to which we have given say 1 Coulomb of charge, then it is your minus 2 Coulomb of charge, then it is given say plus 3 Coulomb of charge, then it is your suppose minus 1 Coulomb of charge. So the total charge, if I consider, it is 1 minus 2 plus 3 minus 1. So that means it is your 4 minus 3 and that is your 1 Coulomb. So that means the charge which will be possessed by the body will be 1 Coulomb. Then charges are induced. That we have already discussed, that if you have a charging body brought close to body without touching it, in that case, opposite nature of the charges will be developed on the nearer end, which are called as the bound charges. And we have the same nature of the charge developed at the farthest end, which we call it as the free charge. So this is that the charges can be induced. Next is the charges are conserved. What does it mean? Charges are conserved simply means the net charge of an isolated system is constant. If you take a particular amount of charge to an isolated system, in that case, that one will remain constant if it is an isolated one. Now here, for the charges are conserved or conservation law for the charges, I will suggest that don't use the statement that the charges can neither be created nor be destroyed there. Okay. Instead of that, just use this one, that the net charge of an isolated system is constant. Now, why we say that? Because if you say that charges can neither be created nor be destroyed, sometimes you may get confused. If you take, suppose, radioactive emission, normally in the terms which is being used, we say that alpha particles are emitted, alpha particles are produced, beta particles are produced. So it is basically the charges are not being produced here. So if you consider that particular statement, charges can neither be created nor be destroyed, you may get confused there. But when we take the emission of the particles, like alpha particle, beta particle, then you can easily explain that as the net charge of an isolated system. If you find some charges, positive charges coming out of the system, definitely there will be some deficiency of the positive charge in the remaining part there. So, and it will be of same magnitude. Similarly, beta particle is emitted, there will be deficiency of the negative charge there in the residual system there. Then charges are invariant. Now, what does it mean? Electric charge of a particle remains unchanged or it is fixed regardless of its motion. Remember, if you take mass, if suppose certain mass is there and it is in motion, in that case there is variation in the mass, that we call it as the relativistic variation of mass there. And here, like suppose if you have m as the mass of the body when it is moving with high velocity, in that case it is given as v square by c square. M naught divided by root over 1 minus v square by c square. M naught is the rest mass, v is the velocity with which the charged particle is moving, c is the speed of light, and m is the mass of the particle when it is in motion. So here you can see if v is there, definitely the m will be different from m naught. Of course, since the speed of light is very large, so this one will be more appreciable if the velocity is comparable with the velocity of light. But of course, for charges, there is no such variation when the charges are in motion. Its charge will remain same. So that is why we call that charges are invariant. Let's now take a few questions on the properties of the charges. These conceptual type questions you can get like, can two lightly charged bodies ever attract each other? If yes, will it not violate the basic properties of charge that like charges repel and unlike charges attract? Second, will quantization of the charges be still valid once the existence of the quarks is established? Third one, an inflated balloon is charged by rubbing it with fur. Will it stick more readily to a conducting or to an insulating wall? And next, do the emission of the alpha and beta particle not violate the law of conservation of charge? And fifth one, two identical bodies are equally charged, but one positively and other negatively. Which one is heavier? Let's take these questions one by one. Can two lightly charged bodies ever attract each other? Now, this is possible. Like suppose if I consider that we have a body which is carrying very high amount of charge as compared to the other body. This is highly positively charged, and this one is also charged there of same nature, but its charging is less. Now, when the two are brought close to one another, in that case, what will happen? Here, there will be the charges which will be induced. So, opposite nature of the charges will be developed on the nearer end, and the same nature of the charge will be developed at the farther. So, here you'll find that there will be negative charge developed. Now, suppose I assume that initially it has the charge capital Q. This one has the charge small q, and the charges which are induced is minus q dash and plus q dash. Now here you'll find the center of the charge on the first body. It will be almost at the center because the charge on the second body was less, so it is not going to disturb much the charge distribution of the first one. But the center of the negative induced charge, now it will be somewhere closer to this body, and the other one, that is the positive one. Like if I consider the positive charge which is developed here, and positive induced charges, if you consider, they will have the center somewhere here. So this is the distance between the charge on the first body, that is the center of the charge on the first body, and the center of the positive induced charge on the second body. And this is the distance here for the first body and the center of the negative induced charge. So as you can see that this distance, when it is oppositely charged, is less than when they are lightly charged or between the like charges. So here force of attraction will be more than force of repulsion. So the net force will be attractive. So net force is attractive. So this is why there will be a force of attraction there between the two bodies. Now, one more thing you can see, charge on the first body was Q, charge on the second body was Q. And after the charges which are induced, it is having the charge say minus Q dash and plus Q dash. So the net charge is still Q. It means the second body is still positively charged. So the two bodies are carrying same nature of the charge, but there is a force of attraction there between the two, as the charge possessed by one body is very large as compared to the charge on the other body. Now, let's take the second part. Force is attractive here. Now, is it violating the basic property that the like charges repel and unlike charges attract? No. First of all, it is the like charges repel and unlike charges attract. Remember here, the question which was there, likely charged bodies, and there is attraction. So between likely charged bodies, there is force of attraction just because like charges were repelling, like this charge, that is the positive charge, and the positive induced charge which is developed here, they were repelling, and unlike were attracting. So here they are not violating this basic property. And second thing, it is the force of attraction between lightly charged bodies. So it is not violating. Let's take next question. Will quantization of the charge still be valid once the existence of the quarks is established? Now, what are the quarks there? Quarks are considered to be the particles which with suitable combination can make electron or can give protons there, that is the charge on the proton there, and they can even give the neutrons there, that is the uncharged particles. They carry the charge as 1/3 or 2/3 the charge on the electron with a different sign there, positive and negative. We have the quarks there. Once the existence of the quarks is established, in that case, because if you say that quantization law is Q equals to NE or plus minus NE, at this moment, this N cannot be fractional. But if you consider the quarks there, in that case, it will be 1/3. Like it will be, suppose you have a particle which is carrying the charge same as that of the quark. In that case, it will be 1/3 of E. So it is not 1/3 of E it will be taken, rather it will be taken as 1 into E by 3. That means the N value there will not be this 1/3, so N will still be integer. That means if I consider at this moment, suppose I have a body which is carrying 2 units of electronic charge. If quarks are established, in that case, the same body's charge, we can write it as 6 times E by 3 if the charge on the quark is 1/3 charge on the electron. So it is not violating quantization of charge. But remember, if you say that the charge on the body is integral multiple of charge on the electron as quantization law, in that case, definitely you will get trapped here and you will say that it will be violating. So quantization law never says that it is the charge on a body is integral multiple of charge on the electron. It only says the charge on a body is integral multiple of certain minimum charge. This minimum charge at this moment is charge on the electron, and after that, if quarks are established, it will shift to the quarks there. The next question. An inflated balloon is charged by rubbing it with fur. Will it stick more readily to a conducting or to an insulating wall? If you are taking a charged balloon and you are bringing it close to a conducting wall there, in that case, the charges will be induced. Opposite charges will be induced on the nearer end, and the same nature of the charge will be there on the farther end. So here, as the opposite nature of the charges are closer to the charged body, so in that case, the force of attraction will be more, so it will get struck there. And if you now compare it with the insulating wall. On the insulating wall also the charges will be developed, but it will be less amount of the charges will be induced. So obviously the force of attraction there, if you are taking, in that case, it will be relatively less there. So the balloon will get more readily struck to conducting wall as compared to a insulating wall. Let's take now, do the emission of the alpha and beta particle not violate the law of conservation of charge? We have already discussed the conservation of the charge. Simply say that the net charge of an isolated system is constant. When we say the charge particles are being emitted, say alpha particle is emitted or beta particle is emitted, and we say that the charges are produced, it is not getting produced there. If you just see alpha particle, it is one part of the system. That is, say you have a radioactive sample from where the alpha particles are emitted, but there residual sample will have the same amount of positive charge reduced. So it will have a deficiency of the charge possessed by alpha particle. So net charge, if you consider, of the alpha particle and the residual sample, it will be constant. Similarly, after the emission of the beta particle, if you consider the charge possessed by the beta particle and the residual sample, in that case the sum of the charges will always be constant. Two identical bodies are equally charged, but one positively and other negatively. Which one is heavier? Now here, suppose we have shown the first body A as positively charged and BA as negatively charged. So the body which is positively charged, it simply means it has lost electrons. And the body which is negatively charged, it means it has gained electron. Obviously, negatively charged body will be heavier than positively charged body. These were some of the conceptual type questions on properties of charges. Let's start Coulomb's law of electrostatics. The force of electrostatic interaction between 2 point charges is directly proportional to product of magnitude of the charges and inversely to square of the distance between them. And this one acts along the line joining the two. So here, if I suppose consider we have the charge, suppose Q1 and Q2 at a distance R, and the force between them is F. In that case, we can write the expression for the force using this Coulomb's law as F proportional to Q1, Q2 and F proportional to 1 by R square. And if you combine them, then you will have F proportional to Q1, Q2 by R square. If you remove this proportionality sign, then in that case we can introduce some constant of proportionality K here. If you consider that in SI system, then this constant of proportionality we can write 1 by 4 pi epsilon. Q1, Q2 by R square is still there. Epsilon is called as the permittivity of the medium. This is the term which will say how the force between two charges gets changed if you are introducing a medium between the two charges there. Now this permittivity of the medium we can express also there as epsilon naught into epsilon r, because this epsilon r we call it as the relative permittivity of the medium, whereas epsilon naught will be the permittivity of the free space or vacuum. So this is your epsilon r, which is your epsilon by epsilon naught. So for epsilon we can easily write it is as epsilon naught into epsilon r. So here we have substituted that epsilon naught into epsilon r. So general expression you can take that 1 by 4 pi epsilon naught epsilon r Q1 Q2 by R square. Epsilon r, what we are calling it as the relative permittivity of the medium. This is also numerically equal to the dielectric constant of the medium. So dielectric constant is another term which we use here, and numerically the two are same. In vacuum, suppose if I want to find out for vacuum, in that case for vacuum the epsilon r will become epsilon naught by epsilon naught, that is 1. So in this particular case, if you see, then F can be written as 1 by 4 pi epsilon naught Q1 Q2 by R square. If you take the two charges, to be kept in vacuum at some separation R. Now this particular term, 1 by 4 pi epsilon naught, numerical value is 9 into 10 to the power 9 Newton meter square per Coulomb square. And if you take the value of epsilon naught, it is your 8.85 into 10 to the power minus 12 Coulomb square per Newton per meter square. And the term which we have used as a dielectric constant or also relative permittivity of the medium. If I take one example for water, the dielectric constant for water is 80. Now what does it mean? If I take the same two charges kept at the same separation but in water, the force will be there in water as 1 by 4 pi epsilon naught Q1 Q2 by R square by 80. It means the force will become F naught by 80, or you can say that the force between the two charged particles at a particular separation when it is kept in water become 80 times less. Remember, you have done electrovalent compound. Electrovalent compounds are the one where you have the positive and the negative ions held by electrostatic force of attraction. If you take the most common example, then it is your NaCl. So here we have the force there between the sodium ion and chloride ion. And another thing is there that the electrovalent compounds are easily soluble in water. Now why they are easily soluble in water? Because as there is dielectric constant 80, so if you put the electrovalent compounds in water, the force of attraction between their ions becomes 80 times less. So the bond becomes weak, and that is why they easily get dissociated. That is why they are easily soluble. Let's now take Coulomb's law in vector form. Now for that we have shown here Q1 and Q2. These are the 2 point charges which have the position vector R1 and R2 respectively. So they have the position vector R1 and R2 respectively there. Now here we have shown force experienced by Q2 as F21 and the force experienced by Q1 as F12. If I consider that F21 as the force experienced by Q2 due to Q1, this will be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12, because the R12 vector magnitude square will give you the square of the separation between the two charges here, and the direction will be R12 unit vector, because this one will give you the direction there. So it is the unit vector in the direction R12. Now unit vector we can write it as your R12 vector divided by its magnitude. So this expression will become 1 by 4 pi epsilon naught Q1 Q2 by R12 magnitude whole cube into R12 vector. Now here one more thing you can see from triangle's law of vector addition. If you consider R1 vector plus R12 vector, so R1 plus R12, this is your R2 vector. As a result, we can write R12 as R2 minus R1 vector. So now if I substitute for R12 here, in that case, it is your R2 minus R1 vector, and in the denominator also it is your R2 minus R1 whole cube. Whereas if I take the force experienced by Q1 due to Q2, so that we write it as your F12. So this is your 1 by 4 pi epsilon naught Q1 Q2 by R1 minus R2 whole cube, and it is your R1 minus R2 vector. Suppose I change the order of this R1 minus R2. So I can write here as minus, and then order we have changed, so it is now R2 minus R1 vector. Now as we have R2 minus R1 vector magnitude same as R1 minus R2 vector magnitude, so what we can say that this will be basically equal to your F21 vector with negative sign. So here we have shown F12 vector equal to minus F21 vector. And this also shows that it obeys Newton's third law. Next is superposition principle. The force on any charge due to a number of other charges is the vector sum of the force experienced by that charge due to the other charges taken one at a time. Now, how you can show that one? Suppose I have the charges here Q1, Q2, Q3, Q4. Now here, if I want to write the expression for force experienced by Q1, in that case we can write the force as F1 vector. That means this is the total force experienced by Q1. And what will be this force? It is the vector sum of the force experienced by Q1 due to Q2. So that we have written as F12 vector. Force experienced by Q1 due to Q3 plus force experienced by Q1 due to Q4. So F1 vector is equals to F12 vector plus F13 vector plus F14 vector. That means it will be the vector sum of the force experienced by the charge Q1 due to the individual charges. Now let's take a few numericals based on the topics which we have discussed so far. So let's take the questions one by one. The first one is two charges Q and 4Q are placed a distance apart in vacuum. Where should a third charge be placed so that the system is in equilibrium? What should be the nature and magnitude of the third charge? Now for this, if the system is in equilibrium, it means net force on each charge is 0. For this, let's take the charge capital Q and 4Q kept at a distance d, and this d is the distance between the two. And suppose if I take a third charge, a small q, which is kept at a distance x from the charge capital Q. So obviously its distance from the 4Q will be your d minus x. If I take now equilibrium of this particular charge Q, so for equilibrium of the charge Q, force on this due to the capital Q and 4Q, they must be equal and opposite. So we have taken 1 by 4 pi epsilon naught Q by x square equals to 1 by 4 pi epsilon naught Q into 4Q by d minus x whole square. And that will give you d minus x by x whole square equals to 4, or d minus x is equals to 2. Now if you take now d minus x as 2x, so this will give you the value of x as d by 3. That means the third charge should be kept at a distance d by 3 from the charge capital Q, so that it does not experience any net force. But since you have to find that the system has to be in equilibrium, so I'll have to take the force on each charge to be 0. So we can take the force on the other two charges. Let's take force on the charge capital Q. So if I take now for the equilibrium of the charge capital Q here, so it is 1 by 4 pi epsilon naught Q by x square, that is the force between the charge capital Q and a small q. There will be the force between the charge this capital Q and 4Q. So plus 1 by 4 pi epsilon naught Q into 4Q by d square. This is 0 because the sum of the two forces must be 0. And that will give you Q as minus 4 times capital Q x square by d square. And if I put the value of x, which was your d by 3 here, then you will get the value of Q as minus 4 by 9 times Q. So the Q should be minus 4 by 9 Q. It means the third charge should have a magnitude equal to 4 by 9 times Q and should have opposite nature, and it should be kept at a distance d by 3 from the first charge capital Q. Next question. Two charges Q and minus 4Q. Now this time see, the charges are of opposite nature. They are kept at a distance d apart in vacuum. Where should a third charge be placed so that it is in equilibrium? Remember, if you have the charge capital Q and 4Q plus, in that case, if I put the charge small q between them, and if suppose it is of same nature, in that case, due to this capital Q, there will be a force of repulsion, say it is in this direction. due to this 4q, again it will experience a force of repulsion in opposite direction. So the net force on the charge q, small q, will be 0 if it is experiencing equal and opposite forces there. So it is possible if it is kept between the two. But here it is given that one charge which is plus q, suppose, and other is say minus 4q. If I put the third charge, suppose it is your plus q in between the two charges, in that case due to this capital Q it will experience repulsive force. Due to this minus 4q it will experience attractive force. So the two forces will be in the same direction, so they can never cancel out one another, and net force cannot be 0 if I'm putting the charge between the two. So if I put plus q charge here, in that case it will experience repulsive force due to this charge capital Q, and due to this minus 4q it will experience an attractive force. So the two forces will be in opposite direction. If magnitude wise it becomes equal, then net force will be 0. So remember, whenever you take the two charges, they are of same nature, then the point of 0 force will always exist between the line joining the two. It will be closer to the charge of a smaller magnitude, but if the two charges are of opposite nature, it will never lie between the line joining the two charges. It will always be outside, and it will be closer to the charge of a smaller magnitude. So here, let's take for this case that you have the charge plus q here, minus 4q at a separation d, and the third charge we have kept it at a distance x from the charge capital Q. So for equilibrium of q, 1 by 4 pi epsilon naught q by x square, this will be equal to 1 by 4 pi epsilon naught force due to this small q and minus 4q. So it is q into 4q by d plus x whole square, because now this time it is your distance d plus x. So you have d plus x by x whole square equals to 4, d plus x by x equals to 2, or x equals to d. So it means the third charge should be kept at a distance d from the charge capital Q. Let's take another question. A charge capital Q is divided into two parts and placed d distance apart in vacuum. What should be the ratio of magnitude of the two charges so that the force between the two is maximum? So you have the charge Q. We are dividing the charge into two parts and we are keeping it at some separation. So we have to see how it should be divided so that the force between them is maximum. So suppose if I take that we have the charge Q, capital Q, divided into two parts as a small q, and another part will be your capital Q minus small q, as it is kept, suppose that a separation is small d. So the force between these two charges will be equals to 1 by 4 pi epsilon naught q minus q into q by d square. This we can write it as 1 by 4 pi epsilon naught q minus q square by d square. So for maximum force, you have to use the concept of the maxima minima. So the first derivative should be 0. So we have taken df by dq equals to 0. So if you differentiate it with respect to q, it is 1 by 4 pi epsilon naught q minus 2q by d square. This is to be 0. So q should be equals to q by 2. So the charge should be divided as q by 2 and q by 2. But again, you have to see that this will be the condition for first derivative to be 0 for maxima as well as for minima. So we have to also see that whether this division will give the maximum force or not. So for that we have taken the second derivative. So it is your d2f by dq square at q equals to q by 2. If I differentiate it again, it is your 1 by 4 pi epsilon naught minus 2 by d square. And here, since there is no term of a small q, so this particular part will always give you a value less than 0 because it is carrying a negative sign there. So this means it has a maxima here. So it has maxima at q equals to q by 2. So the ratio should be Q by 2 and Q by 2. That is equals to 1 by 1. So ratio is 1. We have one alternative method also to do this particular problem. If you do not want to use maxima, minima, or if you want to avoid the use of calculus. Here what we do, we take the force F as 1 by 4 pi epsilon naught Q minus Q into Q by d square. So this is your 1 by 4 pi epsilon naught QQ minus Q square by d square. What we are doing, we are adding Q square by 4 and subtracting also. So if you do that in the second line here, now what we can write, we can rearrange this one as Q by 2 whole square minus these three terms we are putting inside bracket. It is Q by 2 whole square minus 2 times Q by 2 into a small q plus Q square, just to put it in the form of A minus B whole square there. So now it is your Q by 2 whole square minus Q by 2 minus small q whole square. Now this is the expression for force F. If you want the maximum value of this force, in that case this term should have maximum value, and this is here, there are two terms there, like it is there as the form A minus B. For this difference to be maximum, B term should have minimum value there. And what is there, the term in place of B? It is Q by 2 minus Q whole square. Being a perfect square, the minimum value of a perfect square is 0. So it means this Q by 2 minus Q should be 0, or Q should be equals to Q by 2. So that means this part should be Q by 2. So one part should be Q by 2. Obviously, the other part will also be Q by 2. So this is the alternative method to solve this particular problem. Next question. Two small spheres having charges capital Q are suspended by insulating thread of length L from a hook. This arrangement is taken to a space where there is no gravitational field. Find the angle between the two threads and the tension in each string. So for this, suppose it is kept here at a place where the gravity is there. In that case, they will be suspended there due to their weight, and of course there will be a force of repulsion also. So here the length is L. We have taken it to a place where there is no gravity there. So in this particular case here, the force is electrostatic force of repulsion. So it is your F between the two bodies having the charge Q. And now the separation between the two will be your 2L. So obviously in this particular case, if I consider the angle here, as they will be experience force of repulsion, so they will be at maximum possible distance. So this particular angle will be your 180 degree, because it will be straight there. So if it is your angle, if you take, it is 180 degree, and the force will be equal to force of electrostatic repulsion, and this is giving the tension in this string. So the tension T will be equals to F, which is 1 by 4 pi epsilon naught Q square by 2L whole square, because now the separation between the two will be your 2L. So this is the expression for the tension in this string, and the angle will be 180. Next question. Two identical charged spheres are suspended by strings of equal length. The strings make an angle of 30 degree with each other when suspended in a liquid of density 0.8 gram per centimeter cube. The angle remains the same if the density of the sphere is 1.6 gram per centimeter cube. What is the dielectric constant of the liquid? Now for this, let's see what will be the arrangement there. Here we have taken, suppose the bodies having the charge Q there, suspended by means of thread. Here there will be a tension in the string. Suppose T is the tension in the string, and F is representing electrostatic force of repulsion. The weight mg will be acting there, so it is the weight mg acting downward. If you resolve this tension in the horizontal and the vertical direction, then we get the components as T sin theta and T cos theta. If I'm taking the angle theta with the vertical, although it is given in the problem, the angle between the strings is 30 degrees. So that means this particular angle will be basically 15 degrees. So we have taken this theta there as the angle made by the string with the vertical. So now for the equilibrium, the weight will be balanced by the force in the vertically upward direction. So it is the one component of the tension there, that is T cos theta. And the electrostatic force of repulsion will be balanced by the one component of the tension, that is your T sin theta. So let's take that. Here in air, when we are keeping it, we'll have the T sin theta equals to F and T cos theta equals to mg. So tan theta will be equals to F by mg. This is your suppose first equation. If you are putting it in a liquid, there will be a force of buoyancy also acting there. So B, if I take as the force of buoyancy acting on the spheres, and now as there will be a dielectric medium there between the two spheres or the charge spheres, so the force of electrostatic repulsion will also get changed. So this time the force is suppose your F dash. So now in the same case, if I take tan theta, now this will be equals to F dash divided by mg minus B. That is the weight minus force of buoyancy, that will be balanced by T cos theta term, because it is given that the angle remains the same. So now F by F dash if I take, that means if I take this as the second equation, so basically it is your equation 1 divided by equation 2. So it is your mg by B by mg. And if I put for m, it is your 4 by 3 pi r cube, and it is your rho there. So it is your 4 by 3 pi r cube, rho minus g into g in the numerator, and in the denominator for the weight of the body, it is your 4 by 3 pi r cube, rho into g. Rho value is already given, that it is your 1.6 gram per centimeter cube, and the sigma, that is the density of the fluid or the liquid there, it is your 0.8 gram per centimeter cube. If you substitute, you will get the value of K as 2. So the dielectric constant of the liquid will be 2. So this was our discussion today on electrostatics. We'll continue with other topics there of the same chapter, electrostatics, in our next discussion.